This conference will now be recorded.
Okay, I started the recording. We are a couple of minutes in the hour. There's not that many people. They probably I heard a feedback that there was a challenge with the link of the LinkedIn invitation that I sent, which is a bit of unusual, but it might have happened. Anyway, so welcome everybody. This is, of course, the Open Compute Project Foundation Heat Reuse work group. Today we have a presentation by Joe Stagner, who's here at the moment. Before that, Jaime and I would like to spend a couple of minutes explaining what we try to achieve with this group. And Jaime, maybe I'll leave that to you if you want to do.
Of course, I cannot share my screen, so I don't know if you're sharing that or without sharing. Are you sharing something? Because I'm not seeing anything.
No, I'm not sharing anything.
Okay, all right.
I can share my screen if you want.
Okay, so in the meanwhile, welcome everybody.
Yes,
so to this watch stream we started a couple of months ago. We are here to discuss about the heat reuse in data centers, because it's almost an imperative, as we see it, to bring that in the future developments. So the idea of this work stream is to end up building a guideline or white paper with information that could be useful for future development of data centers. So we discussed about the metrics for heat reuse. We discussed about technological challenges. We discussed about how we can monetize the heat reuse, and we also now, for example, completely we are talking about a use case of 1 megawatt of waste heat of data center going into a swimming pool, and what does this mean in an investment context in a data center, and what does this mean from a technical point of view. So we are gathering use cases and successful and unsuccessful stories of heat reuse. Most of them are in Europe, we have to say, but we welcome everybody to come by and explain in this open community what they have done in the past for heat reuse, especially if they come from the US, because we are lack of examples there. There you're seeing actually the small use case we are actually studying. And well, without having anything to share, just yes, we have a wiki page.
Yes, which will be put in the. If you give me 1 second, I'll put it in the chat box.
Go.
Okay.
Great. And we have also an email list where you can email us, guys. Yes, so that's pretty much it. I think nevertheless that John Menosh from Vertiv, he wants to have 2 minutes to comment something very briefly about something they are working at the ACF. I don't know if you want to do that now, John.
Yeah. So I just I had a discussion with John Gross, co-lead for the ACF here, just a little while ago, and one of the things that we've been talking about is reference designs and our desire to collect these so we can provide them out to folks. And one of the kind of overwhelming things that we've understood is that it's hard to get these. So we're going to probably do a little more focus on getting families, or what are basically BIM models of your products. So we're going to probably reach out a little bit more to the vendors to talk about that, and also who can do that for you if you're not going to do it internally. But I think that's going to be a topic for us in the upcoming weeks in ACF. How to both identify who has models that are available that we can get, and also if you don't have models but you have engineering models that you've used to create your products, how to get to BIM that, and then how to get to BIM that is plugged into our OCP or schema, so to speak. But in terms of, for example, we don't call chilled water loops. Chilled water loops, we're referring to it as the facility water system. So with the proper naming for variables or parameters, as they're called. So standardizing that a little bit might make it easier than to create schedules and other things within BIM and layout programs. And we're going to start maybe tackling that as a possible, maybe as a work stream, maybe as just something we produce as part of our part of the white paper. But we'd like to clarify and kind of guide and help the community, especially the manufacturers, along so that we can get a better library of these things for use. So that's all. So thank you for that.
Okay, thanks. For the new guys here on the room, we share this time slot with the ACF workstream where John Menosh is active, so not to confuse things. So actually today is heat reuse, next week will be ACF, and every 2 weeks we just
yeah.
change.
I just added to the chat the link to our wiki page. There you have the calendar. In the documents you have the calendar. You have all the past presentations and all the information about this group. So if you want, please check that out. Two housekeeping things, and then we start the presentation. If you have questions, so please mute yourself during the presentation if you can, because sometimes we have background noises. And if you have questions, feel free to put them during in the chat box, and we will address some of them during the presentation and some of them at the end of the presentation. That being said, and with any further ado, Joe, you have the you can share your screen, right? You are muted.
All right, hello everybody.
Hi. Yes. Okay. So
Can you see my screen? I'm having trouble seeing the split window with both on.
not yet.
All right.
I can't, at least.
Okay.
Me either.
It's not letting me. You have to let me share. I need permission to share.
Oh, I thought I gave it to you already, but let me. Okay. How about now?
Okay.
Okay. Perfect.
Great.
All right. Thanks. Thanks for the invitation to speak, everybody. Just want to share a couple thoughts about potential ways to save energy and money, and obviously reduce greenhouse gases from the operation of data centers. A lot of you probably know a lot of these concepts already, but they came to us at Stanford back about 2009. We were designing a new energy system, and the basic axioms that emerged from our analysis of how to provide energy to our buildings, both heating, cooling, and power, a long time ago, that have emerged since we designed our system and have looked at a lot of other systems, are pretty simple when you think about it now. And that is that when you cool something, you're really collecting waste heat from whatever you're cooling, a data center, a building. And normally that heat is thrown away through the cooling system, cooling towers at a house, your little air conditioner, evaporating and condensing system, and so forth. But if that heat has value, then if you could economically recover it instead of throwing it away and use it to make hot water for your building or space heat, whatever you may need, then it's worth looking at doing heat recovery to collect and use that waste heat, seeing if it's worth the economic value and the sustainability attributes to put in the systems to do that. And so a data center is a big heat sink, as you guys know. You put a lot of electricity into computing and you have a lot of heat to get rid of. And as with buildings, there are a lot of good things that can be done to use less energy to cool, energy efficiency of the building, the cooling part of your PUE and so forth. And the same is true for regular buildings and houses. We like to do the things we can to use electricity to cool them. And so while all that's good and should be done, at some point, it's worth comparing the economic investment of squeezing blood out of the stone to make a facility more and more and more energy efficient in cooling terms versus perhaps investing that money in recovering that waste heat and getting a value from that if possible. So that's what my presentation is about, is to talk about what might be the potential value of waste heat recovery at a data center. Notwithstanding however efficient your data center is, it's always going to have a lot of waste heat. You'll just have less waste heat the more efficient the center is in terms of your cooling and processing. And also talking about the application of cold thermal storage. Since you will be using cooling, a method to collect heat from the data center, could thermal energy storage have a value for that? Again, doesn't matter how efficient you are at your cooling or how efficient your data center is, you're always going to have waste heat. So for that given amount of waste heat, is there efficiency possible for that? So let's take a look. So potential value of heat recovery at data centers. So I'm going to now switch over to my Excel screen. Can everybody see that diagram okay? Hopefully. So it may look a little complicated in the start, but it's a simple and interactive diagram just to give you a relative thought about the value of the thing. So I put in the cost of natural gas at a location at $10. If you're buying it commercially, you might be able to get it for $5 or $6. If you're
I cannot see
paying,
the diagram.
Yeah, we don't see the diagram. It's just a
okay,
blank
I don't
page.
see anything.
let me stop sharing and share the other thing. It didn't switch over for me. So let me go to that and
In this
pick the
case,
right
you
one.
might share the screen maybe and
No, I just had to
and
switch windows. Can you see it now?
yeah,
Yes,
we see now.
yes, now we can
Yes.
see it.
All right, and let me turn these grid lines off to make it easier. So in this example, I've picked $10 as the cost of natural gas, like if you were to put it in a boiler or a water heater at a building to make heat, and electricity, 10 cents a kilowatt hour. They can be higher and lower depending on where you are and that kind of thing. So you could change those easily. But this diagram shows, for example, suppose we have a data center on the left side here, and we're using 10 million kilowatt hours for computing and everything else in the PUE except cooling. And all that electricity for lighting and computing and everything else turns to heat after it's done its work. It's no place else for it to go. It all turns to heat. So if you put 10 million kilowatt hours of electricity into a building, you're going to generate 34,000 million BTUs of heat, because 1 kilowatt hour equals 3,413 BTUs when converted to heat. And then you'd have to have cooling to remove that heat, which is in chilling terms 2,844,167 ton hours of cooling to remove that much heat. So you go over to your data center cooling, and suppose you're using a conventional chiller, and you take that coolant and you heat it up to 95 degrees to go out a cooling tower to be exhausted. Then you'd use about 0.5 kilowatt hours per ton in your chiller and cooling tower if you had brand new, current, clean, efficient machines. Some older chillers and cooling towers will use 0.7 kilowatt hours. Suppose, however, if you used a heat pump and you said, I want the water coming out of my chiller to be, instead of 95 degrees to go to a cooling tower, what if I wanted to be 120 degrees so I could use it to, say, provide hot water for my buildings and restrooms and things? Well, the heat pump would take about 0.7 kilowatts per ton to give you 120 degree hot water out instead of 95. And if you wanted much hotter water, such as Stanford uses, because we have a lot of buildings that were used to receiving 160 or 170 degree water to do the things in the buildings they want, well, your heat pump would consume about 1.5. So if we're just doing regular cooling here of the data center and we're throwing the heat away through a cooling tower, then we're going to use option 1, 95 degrees, and it's going to cost us about 1.4 million kilowatt hours to run our chillers to extract the waste heat from your data center and exhaust it out a cooling tower. Meanwhile, and to say, well, what's the value of that waste heat? If I could somehow use that, does it have a value? Instead of, I'm paying all the electricity in, I'm getting some work out of it. But what if I could get some more economic value out of the waste heat out? Well, suppose right next to the data center, and this isn't the case in many times, but suppose right next to the data center, there is a facility, say a commercial laundry building or a building or apartment complex that uses hot water, a lot of hot water for, baths and kitchens and laundry, whatever it may be. I'll call that an other facility. And suppose that facility just happens to use each year the same amount of heat that your data center is throwing away. So it needs to produce that amount of heat. Well, it could do it with natural gas. So let's say and a lot of them do use natural gas around the country. So to make that much heat in an 80% efficient hot water heater or boiler, you'd have to put in this much natural gas, and at $10 a unit, that'd cost $487,000 of energy for that facility that's sitting next to you to make the heat you're throwing away. Now, suppose you're in Seattle or somewhere and they're still using, because they have cheap 6-cent BC hydropower or Bonneville power. Let's suppose they're using a straight electric radiant hot water heater or boiler. Well, 1 kilowatt hour into a radiant heater or resistive heater gives you 3,413 BTUs of heat out. And so if you're using that kind of method, you'd consume this many kilowatt hours, and at 10 cents, they'd be paying $1.1 million to heat their facility. Now, even though they got cheap, clean electricity, they were a little more energy conscious and smart for the long run. They said, well, I'm going to go ahead and use a heat pump instead of radiant heating or resistive heating. Heat pumps use 1/3 to 1/6 less electricity. Well, you can see that electricity is down about 1/6 of what it was when I was using radiant heating. So that's the first smart thing you could do. But suppose you're doing that, then the value of that energy might only be $270,000. So the point is, for another facility to use the waste heat that the data center is throwing away has a value of, $250,000 to $500,000. So question is, would that be cost effective, over 30 years to find a way to get this waste heat from the data center to this other facility? Suppose you say, well, let's instead of using regular chiller, let's just use a heat recovery chiller that uses 0.7 kilowatt hours. I'm going to get this much heat that I could then sell to somebody else. Well, if they're burning natural gas in those apartments or that laundry facility, commercial laundry facility, that's worth $500,000. So you say, wait a minute, I'm paying $1.2 million for electricity into my data center, getting some good work out of it, but then I could get another $500,000 if I could just put that waste heat to use every year, year in and year out, for as long as that facility is going along. Well, that cuts your electricity costs from $1.2 million down to $0.7 million. So pretty substantial savings in your energy cost if you want to harvest the waste heat with heat recovery chillers, and if you have a host that can use it. What hosts might there be? At Stanford, when we looked, after using all the heat we could for hot water for our campuses, we still had a lot left over in summer. In winter, we didn't have any left over, but in summer, we still had a ton of waste heat available for use. And so we said, now who could use hot water in summer besides our own buildings and student housing facilities? And we started looking at laundry. So the laundry for an entire campus, which includes 2 hospitals, athletic facilities, and a lot of student housing, all of that is done either, in on-campus laundry facilities that run on our central energy system and we're just burning gas and electricity directly to run washers and dryers, or a lot was shipped off-site to commercial laundry. And when we looked at that, we found, geez, if that was laundry was done using the waste heat from the campus district energy system, we could harvest most of that and use it successfully. And maybe Stanford will do that sometime. Well, the reason we didn't is initially the land value around Palo Alto. They didn't want to give up space to build a commercial laundry facility somewhere on campus that could utilize this extra, $500,000 to $1 million a year worth of waste heat we were throwing away, even after we recovered and used everything we can. But the point is, if you have a data center in somewhere where land is cheap, you might ask Aramark or Centus or Mission Linen or someone, hey, build a commercial laundry facility right next to my data center, and I'll share the energy savings with you. Instead of you spending, $500,000 to $1 million a year on natural gas, you could take my 120-degree hot water and do all your laundry with that, and I'll charge you half what you used to use. You know, so there's potential huge energy savings and cost savings if you want to partner with other facilities, and of course, a tremendous amount of greenhouse gas savings. If a lot of those commercial laundries or others are using natural gas, well, by cutting that out, you save a tremendous amount of greenhouse gases. So not only greening your own electricity in, but if you use your waste heat, you could supplant a lot of natural gas use and a lot of greenhouse gases for others. So this is just an example of the value of that. And I'm going to go back to my presentation now. If there's any questions, feel free to ask. But let me go back to picking a different screen to share here. All right. So that's examples of heat recovery. So now I just want to talk quickly about thermal energy storage, because in that previous example or any example, if you have to cool your data center, that means you need to consume electricity, most likely, to drive some kind of machine, whether it's pumps for your brand new liquid cooled solid state servers or a chiller that uses air or water cooling. You're going to be consuming electricity. And the pattern of that electricity use is going to follow the pattern of your heat generation, your computing power, your total facility heat generation. And I presume that that cycles. You know, you maybe have higher and lower periods when there's more or less computing. If you're 100% flat across the board, then thermal storage wouldn't do anything for you. But if your cooling profile is somewhat of a sinusoidal shape, like it is for most, regular buildings, then thermal storage can do a lot by shifting when you use electricity for cooling. Instead of it being a real-time, hour-by-hour thing, you could have a cold water tank and shift when the electricity is used. And this is just an example of that. So if you had a sinusoidal cooling pattern at your facility and you wanted to take the electricity used in the very expensive period time one, which could be the peak of the day today, maybe in 10 years there'll be so much solar power that it'll be a plethora of electricity on the grid, and the sunlight hours and nighttime electricity will be more expensive. But whatever that time is, if there's a time difference in electricity cost, you could use thermal storage to shift from time one to time two when you consume electricity for cooling, whatever those times may be. That's what thermal storage does for you. It also, if you're using chillers, reduces the capacity of chillers you need. So if you had a peak cooling demand of X during a day, then you'd need, X capacity of chillers. Or you could use maybe 0.7X capacity of chillers and a cold water tank. And it's a lot cheaper to build and operate a steel tank that holds cold water than more electric chillers, for instance. So that's why Stanford has a great deal of thermal storage for shifting that stuff. It lowers our peak electrical demand, increases our load factor on the grid. It is a lot cheaper than buying more chillers, and so it does all kinds of good things and could do it for a data center too if you have a sinusoidal heat generation pattern. This just shows an example. If you don't do it, then you're just compounding your sinusoidal demand on the grid with how your electricity is used at your data center, and therefore how the heat's generated, and additional electricity has to be used concurrently for cooling. You can either be on the left column and just make your peak worse and worse, or you can use thermal storage on the right and flip the equation and greatly flatten your electrical demand and your electrical cost. If you use thermal storage, then using it smartly is great. And so we invented a software at Stanford called Model Predictive Control. It's called CPOM, that allows you to then download the weather, predict what the heating and cooling due to external factors might be, not as much of a factor from heat generation in data centers, of course, but still some value there. It basically predicts when your heat demand will occur and will schedule your chillers on when they should charge and discharge from thermal storage to produce the lowest cost of electricity based on demand and commodity pricing. This is an example of how it looks at Stanford every day, where it's predicting heating and cooling and how we should best use our thermal storage to minimize our electrical demand. And we saw great benefits from it, about 10 to 15% reduction in our peak electrical demand and our cost just for using smart software, which I know a lot of you are into that, or at least hosting it. And then this just is examples of some of the charts of the heat recovery we've seen at various facilities. The blue is your cooling load over the course of the year, and in the middle is summer, January on the left, December on the right. And then the red is heating demand. Again, these are more buildings, not data centers. But you can see, Stanford in the upper left with a moderate climate. The lower left, I think, is the University of Illinois, very severe winter cooling or heating loads, but big cooling loads in summer. Office buildings in the upper right are much different than campuses that have all kinds of different facilities like housing and research. They typically have a lot more cooling and not as much heating because they're open in the day, but not at night. But what we discovered through all of these and mapping, number of universities and hot and cold climates around the country and different types of facilities like office buildings in Shanghai to office buildings in Palo Alto, is there's always a good 50% or more heat recovery potential from the cooling of facilities that could be used productively for other facilities. And these are just more examples. All right, now I'm helping design the system for new terminals at Chicago O'Hare Airport in the lower right. And again, in that cold climate, they still can, meet 50% of the annual heating demands just by recovering waste heat from cooling that they're throwing away now. This just shows, again, the general axiom we learned. Applying heat recovery, thermal energy storage, and model predictive control to operate the whole thing was by far, by a factor of 5 to 10, more cost effective, more sustainability effective than applying any electrical microgrid features. So we call it the thermal microgrid, smart management of your thermal energy loads by using your waste heat when you can, using thermal storage and smart software to control the thing, did a lot more for Stanford. It decreased our campus energy use and greenhouse gas by about 80%, whereas the smart energy efficiency you can do in buildings, we have a big program to make buildings more efficient electrically and thermally through insulation and many practices. That's about 20%. So it's the top part of the iceberg. The visible part that people run to is deploying batteries and rooftop solar and making their buildings more efficient. And that can all be good. But hidden below the waterline is all the things I just talked about. Managing your thermal energy smartly is a much bigger opportunity that lasts forever once you shift to these new ways of doing things, and will save you a lot of money and a lot of greenhouse gases. So with that, I will turn it over for any questions.
Well, there's one question from Jaime who's asking how does your thermal storage look like? And I guess was that picture that was in your presentation, right?
Yeah, thermal storage can be done in many ways. A lot of people are, some people are using ice. We used to use ice, but we went away from it to cold water thermal storage. It's just a big steel tank with your chilled water, circulating loop water in it. And there's a thermocline, just like you'd have, say, in a lake or an ocean, where the top 6 feet might be warm, and then below it gets cooler. So, heat rises. And so in this tank, you're going to have warmer water at the top and cooler water at the bottom. So when you send water around to your data center or your campus to collect waste heat, that water might come back at 55 or 60 degrees Fahrenheit. It goes in the top of your tank, and then you can withdraw 40-degree water out the bottom of your tank to cool. And see, it's almost like you're moving the water from the top to the bottom. You're moving warm water in the top, cold water out the bottom. And so you exhaust your thermal tank until it's almost full with, say, 55 or 60-degree water. Then when electricity is cheap, you can turn on your chillers and then go the opposite direction, start pumping that 55 or 60-degree water out through your chiller, cooling it down to 40 and injecting it in the bottom of the tank. So by the morning, you now have a tank of 40-degree water ready for the cooling process again. So it all works with a nice 7 or 8 foot thermocline in between the 55 or 60-degree water and the 40-degree water in the bottom of the tank. And hot water storage works the same way. We have a hot water tank with maybe 160-degree water in the top and 130-degree water in the bottom. So you can get an effective thermocline with a good 10-degree or more delta T separation of water temperature. Now, the reason we went to that instead of the ice we used to use is because to make ice requires about 25% more electricity to cool water to make ice than it just does to make 40-degree water. And so the only people that really use ice anymore are where they're just extremely constrained by space, because ice might take, one half or less of the space, the volume as water to store coolness, if you want to think of it that way. So it's really for those who are extremely space constrained, but most people are using chilled water now because it's easier operationally and a lot more energy efficient.
Any
Just a comment about that. Yeah. So the storage you're using is rather intraday storage, right? I mean, long-term storage is not something you have thought about, or long-term, I mean,
Yeah.
seasonally even.
No, long-term storage, it's almost like lithium-ion batteries. If you want, short-term, 1, 2, 3, 4 days of storage, lithium batteries or water are good medium. But it's really, like you say, it's a diurnal process, 1 to 3 days. If you wanted to try and store up, say, a week worth of chilled water to run a facility, the tanks would be so massive, it's ridiculous. I mean, it's like lithium-ion battery storage. When we looked at ways to provide backup electricity to run Stanford on an island for, say, a 5-day electrical outage on the grid, we need over $1 billion and like 20 acres of lithium-ion battery modules. So you say, no, they're great for overnight or 3 or 4 hour storage, but storing energy in those fashions isn't good. It's not dense enough in lithium-ion batteries for electricity for real huge bulk long term, like winter to summer. You wouldn't do it. Same with thermal storage. It's good for 1 to 3 or 4 days, which is typically all you need anyway, because that's how grid pricing and demand and all that works. If you wanted to go longer than that, there's probably some ways, but I've never heard anybody that really wants to store heat over the long term, except for ground source heat exchange. In places where you're pumping heat out of the ground in winter, but there's no thermal makeup from the natural ground. You just have a big chunk of rock with some perched water that never changes, like in Indiana, for instance, Ball State University. Then you like to say, all right, well, I'm going to cool my campus and inject the heat in summer down below into the ground, and then winter I'm going to suck it back up. So that very low grade seasonal stuff you can do with ground source heat exchange, but that's about the only application I've seen for long-term thermal storage, if you want to think of it that way.
Yeah, that was my question about actually, because I knew that application was existing, and that's why I was okay. Great, Cosimo, please go ahead.
Yeah, so Joe, I'm not sure I've seen it in your presentation, but in the case of Stanford, can you share with us what was ballpark the investment for these, let's say, heat storage facility, and what is the projected return on investment?
Sure. So Stanford, our total project included 3 major things. One was installing a new hot water supply and return piping system to campus. We quickly found out early that we didn't want to attempt to replace our in-ground steam system, steam lines and condensate return. And there's a lot of that back east, older parts of America, district energy systems use that, but it's usually, 10, 12, 15 feet deep. So we copied the European method. Scandinavia does a lot of hot water heating of things, but they use low temperature hot water and they use very shallow pipes. So we use a system from Denmark called Logstore. So we had to put in about 22 miles of hot water supply and return pipes to support 185 buildings. And we had to use great, may I throw a good comment in here, Alpha Laval heat exchangers at those 185 locations. We replaced our steam to hot water heat exchangers with hot water to hot water. So we got much smaller, cleaner, quieter, cool little Alpha Laval heat exchangers to take heat from our district energy loop to heat our buildings. So that part of the whole process was about $200 million, 185 building mechanical room changeouts and 22 miles of new hot water piping. Then we had a new central energy facility. And so that was about, 200 million as well to put in the central energy facility with 7,500 tons of heat pumps, 12,000 tons of chillers, 3 large backup gas boilers to support the hospital in case we ever lost the electrical grid, plus our thermal storage tanks. Plus Stanford made the facility really pretty, architectural to fit in with conference rooms and plants and everybody, so that added a little bit to the cost. So those are the two costs, about 200 million each for the size of loads we have. It could be done probably a lot cheaper, obviously, if you're not in the Bay Area, if you're have a data center somewhere else where it's not quite so expensive labor and stuff. And if you're not working in an existing, research university where you have to be very careful, obviously. So that's probably the most it could ever possibly cost short of NASA doing one. Is in Palo Alto at Stanford, in a research environment with hospitals and everything on the thing. So that's about what those costs were, but it could be a lot cheaper, I'm sure.
And no projection in the return of the investment.
Oh, the return investment was 11 years.
Oh,
so
well,
we
for
looked
400 million.
Yeah. Our present value cost analysis back then, all of our business and campus financial people, we ended up settling on, I think, a 5% present value cost. So when we laid out 30 years of the system and its capital and O&M and energy costs, to find out how much or what the crossover point in time would be between that system and sticking with our gas cogen system, it was 11 years. So 11 years payback on a 30-year investment was pretty good. And it actually was even better because the hot water piping will last at least 80 years. We checked with the Europeans and all kinds of other folks. And so we got our accountant folks to agree to depreciate or assume a usable life of our $200 million piping system of 50 years instead of the 30 they would normally do, even though it could go 80. So they split the difference with us to be conservative. So, we got 30 years free piping out of that analysis. So in reality, the economics are going to be even better. And by
Not
the
to
way,
mention that the price of natural gas went up in the meantime.
yeah, and I was just going to mention, and we got cheaper electricity than we thought. So when we did our economic pro forma in 2011, we were a PG&E end-use retail electricity customer. And so we assumed our electricity would cost about 12 cents a kilowatt hour and gradually go up over time. Well, we got onto direct access in California where you could buy our electricity directly off the market. And we ended up signing our first solar deal in 2015 for a fixed cost of about 5 cents a kilowatt hour for 30 years for half of our electricity. And then a few years ago, we went out to get the other half, and we're just over 2 cents. So we're at, fixed green energy electricity for 30 years of a blended cost of 3.5 cents a kilowatt hour with another 2 to 3 cents in transmission to get it to campus. So under 6 cents a kilowatt hour for 100% green versus 12% and escalating with PG&E on a gradually greening portfolio. So that saved a few $100 million more and pushed that payback even closer.
I've been trying to invite PG&E to this calls for a while, but now I understand why they don't show up.
You got to get on direct access. If you can do your own solar, man, you can save a bundle, and it's fixed and known,
Then John Menosh, you have a question. You can probably unmute yourself and ask the question, which is kind of related, but.
Yeah, well, you might have answered it with how you're buying your power now. But my question was by time shifting a lot of this, which is one of the brilliant things about energy storage and in particular thermal storage, is you can bring your demand charges down. So the question that I have is, was Stanford seeing a demand charge as a large portion of your annual bill, and did you reduce that?
Yes.
Yeah. Okay.
Yeah, so we paid, the transmission component with PG&E and the energy component. When we're on direct access, we pay the same to the market. We still pay PG&E for transmission because we didn't become a wholesale where we could be our own transmission owner. So we still buy transmission from PG&E under their tariffs. When the average California load factor, ratio of peak to total kilowatt hour use, if you had completely flat electricity use, the same amount every hour, you'd have a load factor of 1. The California grid is about 47 to 49%. So the peak's about, twice the base. Stanford used to be at about a 46% load factor when we had our cogen plant. Whenever we turn the cogen plant off, for maintenance and we rely on the grid, we had about a 46, 48% load factor like everybody else. This new system has an 89% load factor between thermal storage and smart software. We're now up to an 89% load factor. It's almost flat. So the very surprising things a lot of people think is if you do clean electrification to stop greenhouse gas, if everybody electrifies cars and buildings and all this, it's just going to overwhelm the grid. And before we got a chance to really think about it, when PG&E heard we were going to probably shut our cogen plant down and electrify our campus to get rid of greenhouse gas, they said, well, what's that going to do to the surrounding grid, Joe? We need a long-term forecast of what your electrical demand is going to be. So we said, well, when the cogen plant was down, we used to draw about 46 megawatts peak off the local grid. And we said, so if we add 20 megawatts of chillers and heat pumps and things, when we start this new system of PG&E, we might be asking me for 66 megawatts of transmission capacity, growing to maybe 80 megawatts over 30 years as we grow. And that's what we told them. But then we started designing the system and modeling it with the software invented. And it said, wow, we could actually be lower. And we modeled that we could be at 38 megawatts as our peak after electrifying. So actually lowering our peak demand on the grid while electrifying. Blew everybody's mind. We couldn't believe it was real, but that's the case. And if you look at our actual peak electrical demand over the first 5-6 years, we're about 38 megawatts. So with thermal storage and smart software, you can actually increase your load factor and lower your impact on the grid, even though you're moving to electrification. It's mind-boggling. As we add more and more direct electric use like electric vehicles and stuff, you'd need, some electrical storage and things to be able to do that. But at least with the thermal part, which is a great part of the electrification effort, and again, the easiest and fastest to do, thermal storage is much better than a lithium-ion battery. I could achieve the same things in terms of changing the electrical demand profile I am with thermal storage with lithium-ion batteries, but it cost about $1 billion and take a whole bunch of space and be far less cost-effective than just using a tank of water. So that's, the other axiom, the extra rule is first deploy thermal storage and then see how much electrical storage might complement that for the goals you want. But thermal storage is so much cheaper and easier, a tank of water than a lithium-ion battery. First, maximize that. But those are the kind of results we saw.
Sure. Now, that said, if I'm not sure, maybe California doesn't do demand charges, but it's load factor based. When you negotiated your contract, does that play into it at all, or is that just a flat charge that you mentioned? Because if you brought it from up to 89%, I mean, you've got almost no demand. And
yeah, so in California, the hideous thing is the big utilities like PG&E, they structure their demand on your peak per month. So you get a reward if you do it. So not being a participating transmission owner in the CAISO system, we by law have to get our transmission services from PG&E and pay their tariff, which does have a big demand component. It's almost all demand if you're not taking commodity from them. And so, yeah, we saved, hundreds of thousands of dollars per year. I think, $500,000, $600,000, $700,000 a year just in demand charges through these changes. I went further and then explained to the campus that if we could get access to the transmission system ourselves, we could lower our PG&E transmission cost by another $500,000 a year because CAISO, I don't know if they've passed the law, but a few years ago they were working on a law to on the general CAISO FERC open access tariff reward demand to shift this 47% average grid load factor to something higher. And they didn't in their transmission fees, they don't do that. They didn't do that. Mm-hmm. So a lot of people are saying, even for wholesale people, we've got to reward demand. If they adopt the law and the structure of rates that their staff had proposed, I modeled it and showed our leadership that if Stanford could get direct access to the transmission markets, we could lower our costs another $500,000 because we had such a great load factor. And to do that, though, we would either have to form our own utility or become part of a municipal utility like City of Palo Alto. So we studied legally a bunch of things. They didn't want to be part of Palo Alto for obvious town and gown reasons. And the best thing we could have done was form an electrical cooperative that would then allow us to have direct transmission service and bypass PG&E. we actually floated that to campus leadership, and they decided not to act on it yet. It was starting to get a little too much out on a branch for them. They've already taken a chance with this new energy system, which has worked great and exceeded all expectations. But to then move to try and become an electrical cooperative and allow faculty and other users to vote on the direction of campus electricity, because that's what electrical cooperative is. Everybody uses electricity, gets a vote. And they didn't want electrical democracy for campus quite yet, even though it would save some money. So that's why we are where we are today.
Joe, that's tremendous. Thank you.
Joe, I actually have another question from Jaime, which is kind of related to, let's say, let me expand that. How was the process to decide this project?
So when we first started out, I joined Stanford in 2007 when they created the Sustainability and Energy Management Utilities Department. The campus wanted to take all the units that were responsible for consuming fuels or energies and producing greenhouse gas or consuming water, producing wastewater, all the things that operationally were part of their electrical or their environmental footprint, put them all together in one, and then say, hey, tell us what options we might have to be more environmental. So that's how the thing was created. And so on energy, the first thing we did was before we even started mapping out our detailed energy usage and costs for the campus, was we invited faculty, students, and the community into what we called sustainability working groups. We said, look, we want to hear all the good ideas from the world. We'd like to take the world's total knowledge right now of ways to produce clean and green energy and other things, how to be more sustainable, get all the ideas from everybody we can, and then triage those for application to Stanford and see if we could then create a system based on all this knowledge that would present us options to take the leadership, say, here's the best minds of the world. They've come together. These are the best ideas between our own staff, research, faculty, everybody. This is all anybody can think of. Here's what we think are the best ideas. So that's the approach we took. But lo and behold, almost all of those suggestions had conventional eyes. They focused on two areas. One, how can we make our buildings more efficient? Or two, how can we green our electricity supply? A few dealt with, how can we green our gas supply, but there's not a lot of options there, as you know. And so that's where all the ideas came from. While all this was going on over the course of a year in 2008 and 2009, I asked the energy department there to start mapping out for every hour how much heating, cooling, electricity the university was consuming. I thought the more granular the data, the more we could explore ideas, more things might be revealed. Big pushback from that. They fought me tooth and nail because they weren't monitoring that. There were some monitors on building consumption of certain things, some monitors of how energy was produced at the central facility, the cogen facility, but there was a big absence of data. So they were able to create the data at the cogen plant by looking at detailed equipment, operating logs, and every hour somebody'd say, all right, chiller 1 was on at 2,500 tons, drawing 1.2 kilowatts. And so they took them months to painstakingly construct an 8,760-hour model of the electricity, heating, and cooling that left the central plant to go to the campus. Well, one of the things we were thinking about while the sustainability working groups were going on, I was doing some reading and things, was heat recovery. So people, think you cool in summer when it's hot and you heat your facilities in winter when it's cold. And that's true, right? And so you think, well, maybe in spring and fall, there's some heating and cooling overlap. And I could do something with that, do a little heat recovery, use some of that waste heat. So we were hoping maybe 5 to 15% potential of our energy could come from recovering waste heat. But when we got the 8760 hourly data and we overlaid heating and cooling, you see those charts I showed you before with the golden heat recovery, and we're like, jaw hit the table. I was like, wow, we could, make 80% of the heat we're using now by waste heat from the way we're cooling. We never thought it could be that huge. So we checked it all. We said, well, let's do another year of data. Maybe this is a weird year for the cogen. Let's not jump to conclusions. So we modeled another year of cogen, reconciled all the cogen energy bills and stuff, and the same thing was holding. So we said, well, this seems pretty promising, but I'm now going to hire 2 external consultants, Jacobs, Carter, Burgess, and affiliated engineers. Am I seeing this data right? Am I insane? What's going on? But they looked at it all. We had 2 peer reviews we paid for, and both said, no, this is true, and a heat recovery system could work here. So that's when we then took it to our leadership and said, we think we're onto something. And that's how we discovered the whole process and modeled it out, designed the system, had many other peer reviews from financial people, engineering people, you name it, professors, just everybody from every walk. Since this was such a big transformative change with a big investment, we want to make sure it's bulletproof, and so did the university. So that's what we went through. Subsequently, when we shared this with the world is when people started saying, oh, this will never work in New York. You guys are in a mild climate. This is a left coast Palo Alto thing. It'll never work in New York. So we started, modeling University of Illinois, MIT, Harvard, different places in cold climates, and found that no, it'll work there too. And the interesting thing is, why does it work in those cold climates? And again, something simple emerges. In summer, there's excess heat. And so whether it's Boston, Chicago, New York, Seattle, anywhere, well, maybe not Seattle, but there's excess heat. And so you're cooling facilities. Well, you're also using heat. It's not for space heat necessarily in houses in Boston in summer, but you're using a hell of a lot of hot water for laundry and showers and cooking. And commercial facilities use it for zone reheat and dehumidification. So there was quite a bit of actual heat use in summer. Nothing near what they use in winter, but enough to make it definitely worthwhile. So if you can recover, you can use 100% of your waste heat in winter and still not meet your heating demand, but any cooling you're doing. And you can meet 100% of your heating demand in summer with waste heat. Even if you were at a house in Boston, you say, I'm zero waste heat recovery in winter, but 100% in summer. Well, you start averaging things out, and that's where you see it's 50%. Why is it at least 50% every year? Because 100 in summer and 0 in winter, and some in the spring and fall, it's kind of averaging out to 100% or to 50%. And that's why all those charts show, 50 to 70% of people's heat could be made through waste heat if they're also cooling. And that's when that axiom was created. We proved it just wasn't a mild climate phenomenon. It'll work everywhere from Miami to New York. It even works better in the hot climates, obviously. In Havana, Cuba, they never have to burn natural gas to make heat in their whole life. They have so much waste heat like I do in southern Florida. I think I modeled houses in Florida. Over 90% of the hot water consumed by houses in Florida could be made with waste heat going out those air conditioners like mine's running right now. It's an opportunity.
Last quick question, because we are running out of time. Are you aware of any systems like these installed in campuses like universities or large hospitals?
Yeah, so Stanford was the first one we knew about. Like I say, I'm helping O'Hare Airport. They're expanding with new terminals, and their new energy system's going to be like this. UC Berkeley is now moving to get rid of their old gas cogen, and move to a system like this. University of British Columbia in Vancouver converted from steam distribution to hot water and is starting to deploy some heat recovery. So it's starting to catch on, but it's taken time. A lot of people have been studying it. The good time for a lot of universities or metropolitan areas to do it is when their existing infrastructure gets towards the end of useful life. It's like, keep running that car until, the cost of repairs makes it intolerable compared to buying the new electric car. That's when you make the shift. So another one's Princeton. Princeton was one of the first to also follow Stanford and say, yeah, this makes sense here. I think Duke University, we also were working with them. They're going to be doing some stuff. So for a lot of them, it's just figuring out how many miles are left in their central plants and when's a good time to direct future investment toward a newer system rather than old technology.
One thing before shutting this down. First of all, congratulations, and I'm very happy to see that this environmental awareness actually made a movement actually in Stanford. But I have just two small questions. One is, what's your next move in Stanford? What is your next project? Do you have something in mind to be even better, to use it for something else? And the second question is, do you think we need, or you need subsidies, or subsidies are needed, are really important for this kind of project? I know we have 2 minutes and it's really a short answer.
Sure. So the next best thing to make kind of the perfect system are two things. In winter, if you don't have enough waste heat from cooling to meet 100% of your heating demand, what do? You either got to burn more electricity or gas to make heat, right? So what's the most efficient way? It's to use your heat pumps and extract that heat from somewhere. That's the most efficient way to make heat. So where can you extract a whole bunch of heat in winter using your existing heat pumps? Well, you can suck it out of the ground, you could suck it out of the air, you could suck it out of a body of water. We modeled it all at Stanford, both ground source heat exchange to feed our heat pumps in winter, and we planned it out and we're going to go to that. But then we looked at our two big large water reservoirs we have in our foothills above our campus, Felt and Searsville. And we were going to expand the Felt reservoir to make it bigger and close down Searsville for fish passage. And so it became the perfect opportunity to move to lake water heat exchange. So we did all the calcs and looked at the environmental impacts of doing heat exchange with Felt Reservoir, and that's the project we're going to go with to completely eliminate natural gas use to make heat in winter or pare it down quite a bit, is to use the big heat pumps you already have and suck heat out of that reservoir in winter. So that's what any of these systems do. Once you do your heat recovery, find a place to get heat that's efficient and environmentally sound, sucking out of the ground, air, or a body of water. At San Francisco Airport, we're recommending that they suck the heat out of the bay, for instance, because they're right on the bay. We didn't want to run a pipe from Stanford through Palo Alto to the bay, for obvious reasons. But if you're right on the bay or something, just like old power plants have been doing it for years, why not use that thermal reservoir? Chicago's looking at ground source heat exchange because they don't have proximity to big water bodies and it's cold air in winter. So that's the first big thing to go completely efficient and sustainable. The second big thing is using the waste heat in summer. You're extracting it anyway and you're throwing it away because you've used all you can for your own campus or your own data center. But my God, 10 miles down the road's a commercial laundry facility burning tons of natural gas. How can I connect these two? So I recommend some of these big data center companies quietly acquire Aramark, Mission, and Cintas and other big laundry facilities to start building a laundry facility everywhere they build a data center. And they have a perfect symbiotic relationship of efficiency. Those are the two big things for anybody. We've asked Stanford students and others, is there a way to make this system better? Is there theoretically any better system than the one I've described? And conceptually, they say no. The only thing we could do is make the components more efficient, make a more efficient heat pump, make a more efficient chiller. But in terms of a basic scheme, nobody yet has thought of any better way to have a total energy system except this kind of scheme. I'm sure there will be in the future, but nobody can think of anything better right now.
Well, I mean, we are at the top of the hour, so people are starting to actually leave. But Paul from Intel, if you are still in the call, you have a question, you can unmute yourself and ask the question.
Yeah, the question was with respect to energy storage. Given that you have the temperature changes, and what's the longest that you can really make use of? In other words, if you had an infinite storage of cold water or hot water, you can make use of it all the time. And with your storage tank, you're trying to create some of that ability to do it. What's the practical time scale that you can make use of that, considering temperature changes through the day and also through maybe seasons or weeks, as the climate is actually changing, heating depth, and changing through the seasons?
So the thermal storage tanks are like large thermoses. They're insulated, and they might lose 2% of their energy per day, if you want to think of it that way. Okay. So, in theory, you could go several weeks at a, 10 or 15% energy penalty for, using that. But again, they'd have to be so big to last that long for most loads that we didn't have a need for more insulation. If I was going to have tanks that cycled over 3 or 4 weeks, I might want to put more insulation on and cut that from 2% down to 1% or less loss through the skin.
Yeah, that's pretty good.
All right. If we don't have any more questions, I'll stop the recording now, and we can stick around for another couple of minutes.